Hello everyone and welcome to our second webinar of the cost action circulability. Today's webinar is on active packaging. I would like to introduce today's chair and Dr. Elena Erens from Sustainable Food Systems, University of College Cork, and myself from Food Science Aarhus University will be the chair of today's webinar. And before starting, I would like to share the few instructions. Chat function is disabled and attendees are muted and their cameras are off. At the end of the talks, we would love to hear from you. And please go to the Q&A bar and ask your questions. And at the end of your talk, we will direct them to the speakers. And also a recorded version of these webinars will be available on the YouTube. So I would like to give the floor to Dr. Elena Erens. Please, Elena.
Thank you, Ilke, for the nice introduction. So welcome all to this second webinar. I'm going to be chairing this session together with Ilke. I'm a lecturer in sustainable food systems, and Ilke mentioned, coming from University College Cork in Ireland. My research is based on looking at sustainable solutions, all the way from new ingredients to packaging as well, more recently. And it's great to be here today and join the webinar.
Thank you, Elena. Would you like to introduce the Selcuk? Or if you like, I can also do that. So our first speaker, today we have two speakers, and our first speaker is Professor Selcuk Yildirim. And he is a professor and head of the Center of the Food Processing and Packaging at the Institute of Food and Beverage Institution in the Zurich University of the Applied Sciences. And he received his bachelor degree in food engineering from Middle East Technical University. And he had an MSc degree from process engineering from Technical University of Hamburg. And then he got his PhD at ETH in the field of the biotechnology. And currently he's a member of the Swiss Food Research Board, and he's a founder and leading research partner of Packaging Innovation Network Switzerland. He also serves for board of the IAPRI, International Association of Packaging Research Institute. He is in close collaboration with industry, aiming to develop innovative and sustainable packaging technologies for optimal food quality and food safety. So please, Selcuk, can you start with your talk?
Okay, let me share first the slides, see if it works. Okay, I hope you can see that.
Yes.
Okay, great. Thank you very much, Ilke, for the introduction. As Ilke mentioned, I'm a food scientist and packaging specialist. I have been working in the last 15 years on the development of different active packaging system for food application, and today I'm going to share some of my ideas and also expertise in that field, and give you a little bit also the link of the active packaging to the circulability, as this webinar is also organized by the circulability cost action. So first I will give an overview about the active packaging system. So why do we need the active packaging systems? Why we are developing new active packaging systems? What are the opportunities, use of active packaging systems for food applications especially? And I'm going to also give a very brief overview of the technologies. We have quite a lot of very nice publications and review papers. If you're interested in, you can read it later on in detail. Due to the time, I will just give an overview what kind of active packaging technologies are there available. And as I mentioned before, I will try to link the active packaging with the circulability and discuss what are the challenges of using the active packaging systems for circular packaging. as well as what are the new opportunities for application of active packaging for to develop new circular packaging systems. So the active packaging, before we start the active packaging, if you look to the traditional package, of course, as a food scientist, for us, the most important role of the packaging is the preservation of the food. And the classical packaging system does this basically just by being a barrier between the food and the environment. It doesn't do anything. It's just a barrier depending on what the food needs. And this, due to this barrier function, it preserves the quality of the food. And it does this because several food systems, they are sensitive to oxygen, or they're sensitive to the humidity, especially. Some are also, of course, for the light as well. And if you look to the here, you see that actually the several of the food systems, they need high oxygen barrier systems. We generally call it, let's say, if the oxygen permeability requirements, let's say 10 and water vapor as well, then you need a high barrier properties. And so several food systems, they need high oxygen and water vapor barrier properties. And during the last decade, there have been several, of course, new packaging materials that has been developed to fulfill these needs. Let me just show you. So if you think about this 10 to the 10, this circle, yeah, and the circle will appear here. So the food, this is the requirements of the foods that require high oxygen and water vapor permeabilities. And if you look to the individual, let's say, commercially available packaging films, maybe alone itself, they do not fulfill these requirements, but we can combine different packaging materials together to be able to fulfill these barrier requirements for the different type of food products. Either combining of the different materials together, laminating them, or just applying also organic coatings or inorganic coatings, we can reach the required barrier properties or even better barrier properties. We even have the possibility, of course, if you use aluminum foil, to further decrease these oxygen and water vapor barrier properties, which can fulfill basically for almost all kind of food applications. So we have developed and we have very nice materials basically to protect the food. And I will say that in the developed countries, in Europe, in the US, in America, we have really very high technology, very good packaging materials to protect the quality of the food. So the question is basically, so why do we need to develop new technologies if we can basically protect the quality of the food well? If you look to the consumer trends during the last decades, I would say, so there's a strong demand on the consumer, from the consumer side, for an increase in health awareness. So the consumers are looking more for natural food products without any preservatives, with less additives, as less as possible, more natural or more near to the natural products. Even they are looking for more, let's say, the less processed products. The harsh processing technologies like sterilization and so on, they are not well accepted. So it should be less processed or minimally processed with less preservation technologies. So that's a trend it goes. And the other trend is in the area of sustainable packaging. So we would like to use in future more circular packaging material, more monomaterial. You remember slides before, I explained to you that we can combine the different packaging materials to be able to achieve these barrier requirements. But if you use monomaterial, then it will be more critical, let's say. Or maybe develop new packaging materials like biopackaging materials, more sustainable packaging materials, or bio-based packaging materials. And the problem with these two trends is that if we cannot use from the food side, if we cannot use the preservatives, if we cannot use additives, or not even the harsh processing technologies, how do we protect the quality of the food? In that case, basically, the packaging should be active and not just only being a barrier, but with this active function, we can compensate these demand here. And in the second case, basically, then when active packaging can also then help. And this means that, for example, for monomaterial or biopackaging materials, we need to improve their properties so that they also fulfill the requirements of such food systems. And therefore, active packaging that has been developed in the last decades, being developed at the moment as well. More, I would say that the first demand, and now more and more becomes also critical or important for the sustainable packaging application. So what is active packaging? Active packaging is a packaging systems that is designed to deliberately incorporate components, as depicted here in the picture, yeah, that will release these components from the packaging directly into the food or into the headspace of the food, headspace that is surrounding the food, or it is absorbing the components from the food or from the headspace of the food. And by doing so, it has a positive impact on the quality of the food. So that's the official definition. And here you see there are two different systems. There's active releasing systems and active scavenging systems. Releasing systems, you can release some substances like antimicrobial agents, CO2, antioxidant flavors to have this positive impact. Or you can scavenge the things like oxygen, CO2, moisture, ethylene, and other to be able to, again, protect the quality of the food. So what are the opportunities to use these materials for food applications? So one of the things that most of the researchers are working on is to use the active packaging to extend the shelf life of the products. Yeah. So this is an important one, but I have the feeling that a lot of researchers is focusing too much on that point. So that's not the only one. That's not the only benefit of active packaging. And I believe that the rest, which we are going to go through now, is also quite important and has a big potential to be applied for. I think if the product has a short shelf life, yeah, if the product causes, let's say, the short shelf life causes the food waste and so on, like fresh produce and so on, I think the increasing of the shelf life is sure important. But today, with the existing, let's say, the technologies and ingredients and so on, we have the right shelf life, let's say. Yeah. So instead of extending the existing shelf life a little bit more, maybe we can focus more on how we can make better products, let's say, instead of extending that shelf life. And like how we can decrease the food loss, or for example, this one, how we can reduce or remove the preservatives from the food formulations to make more clean label products. Yeah? So instead of, because the preservation of the food is a hardware process, so we have different hardwares, and one of them is these preservatives that has been used. But maybe active packaging can help us to remove or reduce these preservatives from the food products. An important one is also that they can enable to develop or to use certain particular packaging types that is not possible before, like biopackaging, which we are going to look a little bit more in detail later on, or using more flexible materials, using more monomaterials, so the transparent windows, and which is all without active packaging will be not possible. It can simplify the processes. Some harsh preservation processes maybe are also not necessary anymore. It can help to present and prepare the foods. Maybe Alexander will talk more about that application, for example, for the food. Or it can help also us to develop at all new products, which was not possible, let's say, with existing classical packaging technologies. And these are the things that we have to keep in mind. It's not only about the shelf life, it's also making new products, better products. So what are the benefits general of these active packaging technologies? Like for antimicrobial packaging, if you look to that can help us, of course, to maintain the food quality of the products by inhibiting the growth of the spoilage microorganisms. It can prevent also organoleptic spoilage. If these microorganisms, they grow, they also produce some off flavors, unpleasant odors, slimes, and so on that can prevent that. Or importantly, also it can contribute to the food safety by inhibiting all the pathogens. There are special antimicrobial packaging system that's only targeting, for example, these pathogen systems like Listeria, Salmonella, and Campylobacter, and so on, and inhibit the growth of such microorganisms. If you look to the CO2 emitters, CO2 within the package we use, for example, as a part of modified atmosphere, it can prevent or retard the growth of microorganisms in food as well. And by releasing, let's say, not only using the modified atmosphere, but by releasing from the packaging, we can reduce the packaging there. There are quite a lot of papers, nice papers, about that, because you need a certain amount of CO2 to have this impact, which means that you need high head space normally. But if you can release through the packaging, then you can reduce this head space and you can reduce the amount of the package that you would need. An important part of active packaging system is the oxygen scavengers, antioxidant releasers. They can prevent the oxidation of the product, prevent the decrease of the nutritional value, and also formation of flavors and odors. I think that's a very important technology, which has a great potential in future. Another scavenger system is the ethylene scavenger. If you remove the ethylene, it's a growth hormone produced by certain climatic fruits, vegetables. So if you can remove this ethylene, you can also prevent the deterioration of these products and prolong the shelf life and reduce the food waste in that application. The potential of these active packaging applications for the different food systems we reviewed 2-3 years ago. We published an extensive paper about that. So if you're interested in, it's also open access, so you can just read the paper and get much more information about that. And if you look to the technologies, we have published also another review paper about the different active agents for food, so which type of chemicals we can use. The detailed information you can find in this paper as well. And this is also an open access paper. If you look to the antimicrobial packaging, there are different technologies. There are natural antimicrobial agents that's preventing the growth of microorganisms, like bacteriocins, niacin, pideocin, antibiotics, organic acids, sorbic acid, benzoic acid, enzymes, lysozyme, and so on. There are ones that are plant origin, like extracts of the spices, thyme oil or oregano oil. And some of the polymers are antimicrobial by themselves from the nature on, or there are some chemical agents that could be used also for food applications. There are the 3 different mechanisms how it works. Either these antimicrobial systems directly release these antimicrobials into the food, or they release first the headspace of the food and then it reaches to the food, or they have an antimicrobial surface. In this last case, basically you don't want to have a biofilm formation on the surface. So the idea is not really to protect the food, but to prevent the biofilm formation where the food is coming in contact with the packaging material. Carbon dioxide emitters, they are generally based on the sodium bicarbonate. As an example, you see here also the chemical structures together with an organic acid, like citric acid, and then the liquid from the food comes, and this reaction which you see it here happens, and then CO2 is formed and released and can protect the quality of the food. Antioxidants, they don't absorb the oxygen, but they are oxidized by themselves and prevent oxidation of the food products. There is quite a lot of natural antioxidants like tocopherols, caffeic acid, carboxyl, and catechin, and so on. They could be also integrated in the package and could be released into the packaging. Oxygen scavenger systems, there's quite different ones here as well. The most well-known is the metal-based, iron-based oxygen scavenger. You will see some packages, or in most of the sachet systems, they also contain the iron-based oxygen scavenger systems. There are some others, inorganic scavengers like sulfite, thiotonite, or photosensitive dyes. There is also high molecular organic scavengers like vitamin C, ascorbic acid, which is working well. Polyamide copolymers or polyolefin copolymers. They are special structures of the polymers that can absorb oxygen. Unsaturated fatty acids and oils have the potential as well, or gallic acid, for example, as a natural oxygen scavenging systems. There is also catalytic systems like metal-based catalysts like palladium catalysts and platinum catalysts, or enzyme-based systems like glucose oxidase. So here you see some example. This is the one that we have developed based on the palladium catalyst as a self-adhesive label. We are also working on the gallic acid, unsaturated oils and fats, and vitamin C as well as an alternative oxygen scavenger systems. Ethylene scavengers are mainly based on the potassium permanganate, which is not allowed to have direct contact with the food. So therefore, it's generally contains a matrix and in a closed environment. And it oxidizes the oxygen basically, and therefore can remove the ethylene, and therefore can reduce the effect of the ethylene on the different food systems. There are some also alternatives like metal oxides, activated clays, zeolites, and so on, but not commercially available. The potassium permanganate is the one that we can buy today on the market. So coming a little bit to the end, discussing the different certain circulabilities. So as I mentioned, I have been working quite a long time on the development of active packaging technologies. And up to now, we were always also talking about what we do, these packagings at the end, but not so much, let's say, in details or in deep. And nowadays, actually, how we handle the end final package and how we treat this package after we use the food product becomes more and more important. Circulability of the product is packaging is more and more important. So we would like to circulate and reuse these materials. In that case, it generates certain challenges, let's say, for the use of active packaging for food applications. For example, the active components. Some of the active components, as I mentioned, could be toxic or could be, let's say, substances that are not allowed to have direct contact with the food systems, like iron or potassium permanganate, which as mentioned. So if we integrate these into package, so that could be problematic, let's say, if you would like to recycle these materials. Or special polymers, I told you, also given examples, some polyolefin base, for example, or some others polymers. They have special groups that are made to absorb oxygen. So this can also disturb the recycling of these materials. Or if you have some other materials like antimicrobial components and so on, active materials, we have to take care how do they fit with the recycling of these materials later on. Amount is also important because if you want to recycle for certain applications, you are allowed to have some other materials, let's say, but up to a certain percentage. It should not be so much. So if we can manage making the active packaging with very less amount of non-toxic substances, it may not disturb the existing recycling systems, and then would fit also the circulability. I didn't show you, but I had some examples you probably saw in the slide. We can apply this active packaging with different forms. For example, we can make label out of that. We can make a sachet out of that. We can make a film out of that. Yeah. So if you think about label, generally self-adhesive labels, they contain also quite different substances. They are the different multi-layer structures as well. So one has to think about, does it fit or not? Can this label be removed later on before recycling or not? If you have a sachet, for example, how it works? Can we still, is this sachet is glued somewhere? Can we still recycle that? Can this sachet be separable from the main package? That is quite important. Another point is the compostability. For example, if you use antimicrobial substances or oxygen scavengers with bio-based packaging materials that are biodegradable as well. So the question is whether these substances may hinder the biodegradation process. So we are now doing one research, for example, to elaborate that. So we integrate antimicrobial substances in biodegradable packages. And later on, we would like to biodegrade by microorganisms. So it's a kind of contradictory thing. So on one side, we would like to kill the microorganisms, on the other side, but after using it, we want the microorganisms kill the package, let's say, and so degrade the package. So it could be challenging as well, which we have to take care of that. But it also, circulability, I believe it also brings some opportunities for active packaging applications. For example, so the companies are looking more monomaterials for recyclability because these multi-layer systems are very difficult to recycle, to separate and recycle. And the monomaterials, so the question is whether we can fulfill these barrier properties of with the monomaterials. So most of the monomaterials alone itself do not fulfill these functions, because barrier is also not, I mean, not only function, should be sealable as well. It should bring the right barrier functions. It should bring also the right functions for marketing purposes and so on. So it becomes quite difficult. Especially the challenging is that the water vapor barrier, oxygen barrier, and light barrier with the monolayer structures. Yeah? And here the oxygen scavengers or humidity absorbers, for example, can help. So that we with monolayer structures, we can still achieve the right barrier systems, and even maybe can also prevent the effect of the light as well. Another opportunity will be the use of the biopackaging. For example, biopackages generally do not have the also good barrier properties, especially not good water vapor barrier properties, but some not as well so perfect oxygen barrier properties. So here again, the oxygen humidity absorbers and oxygen absorbers could help to apply this biopackaging as well. And generally, the bio-based packaging materials are a little bit more expensive compared to the traditional packages. So here, if we can also add some value, so it's a bio-based packaging, but edible at the same time, or bio-based packaging have antimicrobial properties at the same time, so protects better and so on. So by adding these values to the active packaging system, we can let's say make it possible that it comes into the market with an acceptable price for that. Another possibility will be not only the polymers, looking also at the papers, let's say supporting the papers to bring certain advantages like also barrier properties through the oxygen absorbers can also help to use other sustainable materials for food packaging applications. So as conclusion, in general, active packaging has a huge potential for the preservation that we have shown already to develop sustainable, healthy, and high quality of food. But and there are some certain challenges of using of these active packaging systems for circular packaging system for circular economy. But circular economy brings also new opportunities for active packaging applications. So I would like to thank you very much for your attention. And last but not least, I would like to remind that between 26th and 29th of September, there will be the first circularity conference. So if you did not register yet, it will be online. If you did not register yet, you can still register for this conference. I'm looking forward to also see you and discuss you other topics as well in this conference. Thank you very much.
Thank you very much. Such an excellent presentation that gave a great overview of active packaging. And I would like to ask attendees to please, if you have any questions, you can type that on the Q&A box that it appears on the bottom of your screen. And while we're waiting a few seconds to get some questions, I suppose I will start asking one question. It might be a little bit general in this case, but I just want to relate active packaging and sustainability. And I'd like to ask you the ideal material. If you're thinking about ideal material to use active packaging and having circularity and also sustainability in the background, what's for the attributes or the characteristics of that material?
Mm-hmm. Well, the active packaging has a function, so it should fulfill that function. Let's say if it's antimicrobial or if it is oxygen scavenger, let's say it will fully function to protect the quality of the food. That was the one constraint. And the second constraint, as I mentioned, so it should not disturb the circulability of the packaging, I would say. And so because otherwise then we generate problems. Imagine that if we generate like PET bottles, yeah, with some oxygen scavengers inside to be able to apply to certain applications, but then it hinders the recyclability of the PET bottles. That's not the option, basically. So it should fulfill the both functions.
Very good. That's great. Thanks very much. I'm just seeing we have not received any questions from attendees. So please, if you have any, just type those. Oh yeah, we have received one question from Daniel, and he's asking, is there any challenge of using antibiotic, any chemical in the antimicrobial packaging nowadays in food industries related to safety?
Right. So generally the trend is more using natural antimicrobial components for food packaging applications, using of antibiotics or the chemicals. There are quite a lot of different challenges. The first one is the acceptance by the consumers. That's not so high as we can imagine. And the second one is also the legislations. If you use any kind of chemicals, basically then it should be food grade chemicals. So if there is any antimicrobial substances that you are not allowed to add to the product directly, then you are also not allowed to add through the packaging. So the legislation already limits the amount of the materials that we can use. So for non-food applications, so there's other opportunities. There's like the silver-based antimicrobial systems that is used quite a lot in hospitals, where you need more hygienic conditions. But for food, it is really clearly defined that it should be food grade. It should be something that you can directly add. And a lot of antimicrobials or chemicals or antibiotics, we are not allowed to add directly into food, therefore we cannot use. But the natural ones has more potential, let's say, because there is less risk of using this, like essential oils, for example, or sorbic acid and so on, to add through the package.
Great, thanks very much for that. With this, I would like to move to our second speaker. So I would like to introduce Dr. Alexander Bardenstein. And Alexander is a business area manager for packaging materials and at the Center for Plastic and Packaging Technology at Danish Technological Institute. He holds a PhD in solid state physics, and he has more than 20 years of experience in industry-oriented R&D. He has gained a broad experience in plasma processing of packaging materials, also in packaging for e-commerce, microwave decontamination of food, and other topics from cross-disciplinary research field of technical physics, applied physical chemistry, and active packaging technology. So the floor is yours, Alexander. Thanks very much.
Thank you very much, Elena, for your introduction. Thank you. I will start sharing my presentation. Just a sec. Yes. Good. Here we go. I hope you can see the presentation screen, right?
It is perfect, Alexander. Thank you.
Thank you very much. So today I have quite an interesting topic for you. Advanced active food packaging solutions for use in microwave ovens. In his presentation, Selcuk already mentioned that surprisingly, it's not only active packaging that is used for preservation or protection of food, is active packaging or uses active tools for that, but also for heating and cooking of food, active packaging of a special kind that is called microwavable packaging can be used. And some people say that this is a gray shadow zone of active packaging. And that's really correct, because this area is really different from other active food packaging areas. But let me first start from a short introduction to microwaves. I will really make it very, very short, because I believe most of you know what it is about. Just to remind that microwaves are not by physical nature different from any kind of electromagnetic waves. And on the picture down to the left, you can see actually how large the frequency area is for microwaves compared to, for example, the area where our vision is for visible light. We are really covering like 3-4 orders of magnitude, 3-4 from 10 in minus 1 to 10 in minus 4 meters when we are talking microwaves. And that's a really huge area, and it's used for many, many applications. Some of them we use every day without even actually making clear for ourselves that we use microwaves both for heating buns and ready meals, and using it for communications, for example, as Wi-Fi, as mobile phones, using both 4G and now 5G and Bluetooth and many other things. And we use it for radars, we use it for many, many other things. But of course, application for microwave ovens is most known for normal people, for consumers. We all use microwave ovens at home. So the question is how, actually, it would be interesting to look at how microwaves are related when we use them, for example, for communication, and when we use them for heating food. And if we would be able to collect 5,000 mobile phones in the volume comparable to a cavity of the microwave oven, which we have at our kitchen, then we could probably heat up our food using mobile phones. But then it becomes really exotic. So from this a bit funny introduction, I would like to go for packaging applications. So how is packaging for microwaving different from other packaging applications? First of all, most of foods intended for microwave preparation, intended for microwave cooking or heating, these are convenience products. And this means they have to live up to the demand for convenience food. First of all, we all highly estimate our time, and therefore the preparation time should be very short compared to, for example, when we cook it in a conventional oven or just fry it on a pan or something like that. Second, nutritional values. So basically, we do not sacrifice the nutritional value of food. It doesn't make sense to eat convenience food if it doesn't fit. So this means nutritional value is a very important thing. And also great food experience. If you do not come up with proper packaging, with a proper food quality product, no one will buy it. And there are plenty of examples. Convenience food is frequently on the shelves of supermarkets, but people avoid buying them for a very simple reason. Sometimes quality is really, really low. And this happens frequently because we don't know how to pack food so that it works well in microwave. And this is why designing of food products that would respond well to microwave cooking is actually quite a challenging task. As one of the journalists working for food technology, her name is Kate Bertrand, I met her once, she once said, food products that respond well to microwave cooking is a mixture of art and science with heavy emphasis on the science, which means that in contrast to many other packaging applications, actually microwave packaging is the area where almost everything can be predicted by either computer simulation or sometimes really simple theoretical calculations, because behind microwave heating is a physics, and physics is universal and works very well. But we have to get use of the physics behind microwave. And as for the food quality, as for the retention of the nutritional value of foods in the microwave, the scientists believe that microwave is intended to better retention of the food quality, mostly because microwave heating really makes preparation time short. And one of the problems that people see in microwave cooking, and that has to be addressed by packaging, is that heating is highly inhomogeneous if you do not take measures to make it homogeneous. For example, on this slide, you can see quite a popular breakfast option, and people in the United States know it very well. It's called a breakfast sandwich. Here you have a bun with three-component filler. It's a meat patty, then egg patty, and then slice of cheese. And some companies, they offer this as a frozen food. They pack it in just in a plastic bag, okay? And the plastic bag is, of course, fully transparent for microwave. So you do not have any option to control microwave heating. That's the food itself that controls the heating. And then what happens is that frozen egg patty doesn't want to absorb microwaves. And then when you get your sandwich out of the microwave after a minute or two, you see that bread is already stale. It's not eatable at all because starch is stale and crystallized, while the egg patty inside still is cold and sometimes even frozen. So this means that packaging for microwavable food at least should enable even heating. And then we come really to something that is distinguishing microwave packaging, true microwave packaging. The true microwave packaging is always active packaging, because passive packaging, which is transparent to the passage of microwaves, cannot make any difference. That's the food that controls the heating, not the packaging. Other shortcomings which are known for passive packaging that doesn't have any control over microwave field is the phenomenon called thermal runaway. Imagine you have something frozen, you put it in the microwave, you quickly create a hot spot in it, and then from this hot spot, you have full absorption of the energy, really in a localized area of the food, and the rest might even remain frozen after several minutes of heating, while the spot where the thawing process went first becomes overheated. And this is called thermal runaway, simply because you do not control the temperature. It runs away without any control. Another phenomenon is called water pumping. I will get back to it later. And it's essentially something that impedes crisping and browning in the microwave oven, which is a known fact, and makes impossible to initiate Maillard reaction that is needed for crisping and browning the food. Therefore, we say that true packaging for microwave applications, that the packaging comprising, first of all, a barrier material, because it's still packaging, it has to preserve the food. Second, it has to be thermal insulation as one of the components, because otherwise you heat first food and then food transfers its energy into the air inside the microwave cavity. And this means that you actually lose the efficiency of microwave heating. But there are two components which distinguishes microwave packaging from anything else. That's the reflectors of microwave energy, which are also called shields, and the susceptors, which Selcuk mentioned in his presentation already. Let's first make a short stop on shielding packaging. In reality, shielding in most of the modern microwave packaging is realized by using relatively thick sheets of films of metal, which are thicker than 3 micrometers, aluminum, sorry, which are thicker than 3 micrometers. Using, for example, silver as a packaging component would bring this down to 0.5 micrometer, but it would be also rather expensive. So this means that one of the most important materials for implementation of active microwave packaging is actually aluminum. But then these shields or reflectors of microwave energy can be distributed to two groups. One is called continuous shields, and this means that basically the size of the shield is larger than half of the wavelength of the microwave. And another type is perforated shields. It means basically that it is a sheet, a metal sheet, with the penetration holes in it, with a pattern of penetration holes where the microwave energy still is able to penetrate. And on the slide, you can actually see how this packaging, how these shields can be implemented. I also have some samples here. One of them is also shown on the slide. Basically, what we have here is a utensil or something that can be considered as a reusable packaging. And then we have a tray that is absolutely transparent for microwaves. And when we put it inside this tray, and then we have a sealing film that also have a pattern of perforations. Then it becomes actually active packaging that allows homogeneous heating, for example, of ready meals, which could be put on this transparent plate. And you can see an example of how this packaging could improve the homogeneity of heating. So I would say that this is a perfect concept for something that we could call reusable packaging. Another example can be seen as a simple tray. It's just a prototype we developed for one of the companies who is interested in reusable packaging. So this is basically a tray that you can close. It has certain barrier properties and it can preserve food in the fridge. But then imagine you have to heat it in the microwave. Then there is another tray. You can put it inside. But between these two trays, you can put an active component. This is a shield with the perforation pattern that actually can control the heating. Moreover, on top of the tray here, you can put something else, which we will talk about a bit later. This is exactly the microwave susceptor. And then it would mean that, for example, you can put a piece of lasagna in this packaging that will be homogeneously heated. But what is more, it will be crispened by this component here that is called susceptor. Again, we will talk about it later. So a bit more about recyclability of the active packaging, and I will get back to this question once again. Of course, the recyclability is impeded. The recyclability is difficult because you have so many different components. However, as I said, first of all, reusable packaging could be an option. And another thing is that some of the components of, for example, shielding packaging, they are not more difficult to recycle than, for example, liquid packaging boards, which have metallization. For example, Tetra Pak material that is used for juice packaging or something like that. It's basically the same problem. So you have a material, for example, that has a cardboard on both sides and then a thin film of aluminum that have to be separated. Cardboard should be repulped and aluminum should go to remelting. So it's in principle doable, but the problem is that the recycling systems nowadays are not too advanced to do that. Then let's get back to something we already mentioned. It's called susceptors. So what's susceptor? Susceptor is an active microwave packaging material that allows partial reflection, partial transmission, but what is important, also absorption of microwave energy and conversion of this energy into heat. The first commercial susceptors were in the form we use them now. They were invented in 80s. And since that time, I think there was no significant progress in development of commercialized solutions for susceptors. In reality, I would say that the invention of susceptor, and you will later see why I'm saying that, is in fact one of the, or let's say the most important advancement in microwave packaging after the invention of microwave oven itself. Because it's really a relatively cheap material that allows you some things that would never be enabled in microwave oven without them, like crisping and browning. So susceptor is a very thin metal film, basically. The thickness of aluminum film, for example, should be around 1 nanometer in order to make absorption of heat by excitation of so-called eddy currents. But of course, it has to be a packaging material. Therefore, what's used is metallized PET films which are laminated on either cardboard or paper, basically to stabilize the material. Obviously, aluminum foil with a thickness of 1 nanometer cannot be suspended in the air. It won't be packaging. Therefore, it's very important to have this component. And the working temperature of the susceptor is around 220 Celsius. This means that it allows crisping and browning applications. And once again, the susceptor is partially transmitting microwaves, partially absorbing and reflecting it. So what's reflected is 25% fraction of microwave power. What's transmitted into food through the susceptor is still 25%. And what is absorbed and converted into heat is 50%. And it's very, very crucial. It means that in some applications, actually, we can't really, and we will talk about it right now, we can't really do anything with such a susceptor apart normal heating in the microwave. I have a slide explaining actually how this susceptor works. It requires a bit of insight in the physics, but basically, I should say that a commercial PET susceptor has a very important feature. It can be stabilized at a certain temperature, and it will keep this temperature during the heating process. And it happens because of the change of electrical resistance, of electrical impedance of the aluminum layer due to phase transition from A PET to C PET, from amorphous PET to crystallized PET, that happens during the preheating stage. I will not go into details here, but it's important to mention that this is really a system with a feedback that is provided by let's say, a property of polyethylene terephthalate to have a phase transition at the temperature slightly above 880, 890 degrees. And its transition into crystallized polymer. So why this, as I mentioned before, why this commercial susceptor is not always good? Exactly because of this 25% of microwave energy that is transmitted into food. This means that the energy that partially penetrates into the food hits it, as people say, from inside. In reality, it's not hitting from inside, it's just a penetration of microwaves deeper. And then, if the food has a high water content, you simply heat the interior and you pump by means of thermal enhanced diffusion the moisture from the interior of the object to the crust, to the surface of the object, where it has a contact with the cold air in the microwave. And then it condenses there, and then it soaks the surface of the food simply by moisture. And then, of course, there is no question you cannot really crisp or brown the surface. And this means that for advanced applications of susceptors, you need something else. You need a construction that would prevent absorption of microwaves in the food and convert as much as possible of microwave energy into heat. And here we go. A few years ago, we introduced a double layer thin film susceptor concept that essentially uses commercial susceptor films. And when we developed a few commercial applications for that, we discovered actually that these kind of materials already been patented back in 90s. But let me first stop for a short while on the properties of these double layer susceptors. Basically, the calculations you can see on my slide, they really show that using a double layer susceptor construction, you're able to absorb 66% of microwave energy and convert it into heat, while the amount of microwave energy that is transmitted into food is just 7%, compared to 25. So this means that you can really apply, you can really emulate the conditions of conventional oven inside. And this is a very nice feature. And then when we analyzed the, so to speak, the IP landscape around this double layer susceptor, we noticed a few things. First, which we not covered before. First of all, most of, or let's say, all three of these paintings you can see on this slide, they are devoted to rigid packaging materials, which are not flexible, while as you will see later, we have developed a flexible material that allows some new features and allows more flexibility in packaging applications. And then we also noticed that this rigidity of the packaging material with double layer susceptor can cause actually local overheating. So we aimed at something that is more flexible. And what you see on the slide in real life looks like this flexible double layer susceptor material laminated on paper. It's almost a monomaterial, simply because when you heat it up to the temperature above 200 degrees, the paper and the susceptor, they get separated from each other. So there is not much of effort needed for mechanical recycling. And the rest of this material is just PET, polyethylene terephthalate. That, of course, is contaminated with metal, but then it can be converted into something else than food packaging and basically being put in the recycling loop that way. And then we use this susceptor for several quite striking demonstrations and commercial applications. Like, for example, French fries, which we crisp from frozen, or cooking a whole potato tuber, like we would do it in the oven, having a crisp crust or having a crisp crust of potato. And another application you can see here is a salmon pie. So it's a dough pastry, it's a flaky pastry, and then you have fish inside. From frozen, we can bake this pie in this susceptor material. Another application that deserves attention is spring rolls. A lot of people tried actually to create a well-functioning microwave packaging for spring rolls, but it never happened because of the high moisture content of the filling in the spring roll. We managed to do it using this susceptor material. And finally, I would like to say that actually almost any kind of food can be, which you would conventionally prepare on a pan or in the oven, basically be made, let's say, functioning well in the microwave oven using active packaging, using, for example, developed susceptor materials. And it includes a really wide range of foods like sandwiches, like nuggets, like fish and chips, schnitzels, and so on and so on. What impedes commercial applications of active microwave packaging? Of course, high cost, relative complexity, lower recyclability, which I already discussed. On the other hand, we believe that the more, for example, of reusable packaging will be introduced in the near future, and there are some tendencies that show that it will be, the more possibilities for implementation of active microwave packaging we would see. And that was a very, very simple and fast summary. So this is why I highly encouraged, if there is an interest in development of active microwave packaging, to go deeper into it. And for further reading, I would recommend some books, which you see on this slide. I hope the slides will be shared with you, so you will have a possibility to read it. Thank you very much for your attention. I don't know if I have any time for questions.
Okay, thank you very much, Alexander, for a very fascinating talk. Actually, we run out of time, but and I don't see any question in Q&A bar, but still I encourage the attendants to type any question in Q&A. So I have the one question actually. So how do you see the future of the nanoparticles in the microwave packaging applications?
Actually, I don't see a future for application of nanoparticles, but what I do see a future for is microparticles. The thing is that if you look at the size of aluminum particles, then there is a resonant absorption of microwave energy in the particles with a size of around 12 micrometers. So this means that in principle, the susceptor with a controllable temperature could be developed, or let's say could be implemented on the basis of the particles with the approximate diameter of 12 micrometers. We have carried out some experiments in the lab, but of course, the real application of this material would require a lot of approval efforts and so on and so on.
Yeah, I agree. So thank you again. Before concluding our today's webinar, I would like to encourage you to visit our circulability website, which is circulability.org, for further infos and any updates. We have always the updates for upcoming events. And as the Selcuk mentioned, we are organizing our first circulability conference in September 26th and the 29th, and you are very welcome to contribute. The abstract deadline will be closed on the 30th of June. And also we will have our upcoming webinar in September. So please keep eye on our circulability website. And thank you to all attendees and to Alexander, Selcuk for your talk, and Elena for co-chairing this webinar. And yeah, thank you very much. I wish the very good weekend to all of you.
Thank you.
Thank you.
Thank you very much.
The same to you. Bye.
Thank you.